Hi everybody, this is EDMM 2001. I recorded the lecture about a week ago or so, and I was getting ready to upload it to the e-learning site. And I thought of a few things I wanted to add to it, so I put it in this little clip to put at the beginning. First off, sorry that it's recorded. Next week will be in person, the way I'd prefer it. Since you're not able to ask questions in real time with this lecture, what I plan to do is in the next week with the in-person lecture, I'm going to spend a few minutes at the beginning to recap what was in this first lecture so that we can go through some problems and you can ask questions if there's anything you have trouble with. So as you're watching the lecture, if there's anything that you're not clear on, write it down. And then bring that to the next week's lecture and you can ask questions on it. Also, to be fair, at the end I talk about there's 2 assignments that I've assigned for this week, a homework assignment and a quiz. I'm going to extend the due dates on those to go past next week's lecture. So that way you'll have the ability to complete them after you've asked any questions. I would suggest, if everything makes sense to you, that you do the assignments early on while it's still fresh in your mind, but you'll have that option. So with that said, let's move on to the lecture. Hi everybody, this is EDMM 2001, Applied Electricity. This is going to be a fun course. It's going to cover all the practical things that you'll need to know once you graduate and you get your first professional job. The types of components you're going to need to know and understand how they work, especially the terminology, so that when you're having a conversation with an electrician or electrical engineer or a production maintenance person, that you'll understand what they're talking about and have a general knowledge of working knowledge of the types of things they'll be talking about. The lectures and labs. So this first week is the only one that's going to be remote. All the following ones are going to be in person. So I hope to see you there. There's no lab this week and this week only. Next week, we'll be back to in-person lectures and in-person labs. There will, though, for this week, I'll have a quiz and a homework assignment that will be posted for you, and we'll get into that later. Now, on March 3rd, that's Spirit Day, we won't have a lecture or a lab. The following week is spring break, so we won't have a lecture or a lab then either. So you'll have 2 weeks off on that. Just so you know, don't show up. I won't be there. Grading, this is all in the syllabus. Obviously, you notice that the lab activities count for a lot. So show up for the labs, do your best in those, and you'll be fine. Now, we don't have a book for this class, but what I am going to do for each lecture, I'm going to post in the e-learning site a synopsis of the lecture. Practice problems, all sorts of information in that. You can use it as a study guide. So that's what you'll use for reading. But since we don't have a book, we do need, though, a digital multimeter. You'll be using that in the labs to take measurements and evaluate and troubleshoot different situations. So you will want to get one. They aren't too expensive. In fact, they're probably less than the typical book that you'd buy for a class. So it's not too bad. Now, you can get whatever one you want. It really doesn't matter to me. I'm just giving suggestions here for anyone who has no idea what to buy. I wanted to make sure we got decent ones, because you can buy really, really cheap ones, but they will probably cause you more trouble than the money savings is worth. Here, I have the X-Tech EX330. That's a decent one. The other one is the Klein MM420 or MM400. I have that one here. They're both good units, and they aren't very expensive. You can see they're on Amazon. They're not too bad. If you wanted a slight step up, Amprobe is a subsidiary of Fluke, and they make this as a discount model that's very similar to the Fluke models, but it's made in China. But it's still a little bit more expensive, but it's a nice unit also. If you want, you can get a Fluke. A lot of people want the best equipment they can get, and if you spend between $200 and $1,300, you can have a Fluke too. For this class, it wouldn't be necessary. But if you're wanting to buy something because you believe that you'll be using that as a tool off in the future, and you want something that's specific to you, or if you already have a multimeter and you like using it, you're familiar with it, and it works well for you, then that's fine. The guidelines for me, if you're going to buy one or you already have one, these are kind of the recommended requirements for what you need. Fuse protected is really good. You will probably blow a fuse in the class at some point. So when you buy one, I would buy some fuses that go to that particular unit. If you're measuring voltage and it's set in amps, it'll probably blow the fuse, and then your meter won't work. So you're going to have fuses on hand. I usually have a few on hand that, if you're in a bind. But when you get your unit, figure out what fuse goes into it and go down to the hardware store and also buy some fuses. I think the big box stores also sell digital multimeters. They may meet these requirements too. You'll just have to look. So you want fuse protection. You want a digital readout. The really cheap ones have an analog needle that you're not going to get very accurate readings with that. It's difficult to use, and they're kind of a pain. It should be able to measure all the basic things: amps, volts, ohms. Have it where it can do diodes and capacitors, and also it's important to have it be able to do continuity. And we'll go into that when we start talking about the digital multimeters. Auto ranging, it's a really nice thing to have. Otherwise, you'll have a meter that will have a whole bunch of dial positions. You'll see them on Amazon. The less expensive ones will have a ton of different selection spots that you can select. And you have to pick the one that goes with the amount of current that you're reading, which takes longer and is kind of a pain in the butt. So if you can get one that's auto ranging, it'll just save you time. It'll be a lot easier. Safety, got to go over it. No one likes going through it, and you probably, if any of you done internships or worked in a factory, they usually give you this safety lecture, and it's important. It's boring to talk about, but when you're in a situation where it's like, what I do in the next 2 seconds determines whether I keep my hand or my vision, you'd be really glad that you went through this and thought about it some. Now, safety, the most common the causes of electrical injury, tools. You got your hands in a panel, you're working on stuff, you have a metal tool, and you either drop it and it comes in contact with two probes and you get an arc, or just while you're working, you got a screwdriver in there, you're in there really tight, side of the screwdriver hits another spot, another terminal, and you get an arc, and it can cause a lot of problems. It can literally melt the screwdriver. Using the wrong tool. You see this all the time. This is the one you should really pay attention to. I see it where, all right, I need a screwdriver to remove this part. I don't have a screwdriver. Oh, I'll just use my jackknife. So you get your jackknife out there and you start, and it'll do it, but you're just so much more likely for that tool to slip out off the screw and touch something else and cause a shock, that you're taking a huge risk in not using the right tool. The right tool makes all the difference, make your work a lot easier. So plan ahead, have the tools that you need to do that work with you so that you're not just going, well, I'll just use this. Biggest one, being in a hurry. Shift's almost ending. I got to get this done. We're going out to dinner later. I just got to get this done. And so you cut corners or you rush through something. That's when most accidents happen. If you hear anything on this, it's don't rush. Rushing will get you in trouble. The the time you save, you'll end up wasting in the ambulance and at the hospital. So just take your time, do things the way they're supposed to be done, and you'll be a lot safer. All right, what is dangerous? Most accidents happen at 120 volts, regular voltage that you have in your house. A lot of people probably figure most really serious accidents happen at 600 volts or 4,000 volts. But this is just more common. And this 120 volts can bite you just as good and stop your heart just as easily. So be real careful. Just because it's a lower voltage, don't assume that there's not a hidden menace behind that voltage. It's the amperage that gets you. So voltage, yeah, it's important, but really it's the amount of electrons going through your body that's going to cause the damage. A lot of you're familiar with static shock. Wipe your feet on the floor, then touch a doorknob and you get a little arc, a little spark. Doesn't really hurt much, and that's because there's not many electrons flowing through that. It's a small electrical buildup. It's when you're working with a system that has the potential for a lot of current to flow. That's when you're going to get in trouble. And that usually follows with voltage. If you're running 600 volts, it's probably a very large system that has a very large amperage capacity behind that. So usually amps and volts go together, but high voltage doesn't necessarily mean that it's going to have the current there to really cause problems. Up to 8 milliamps, you'll feel it, give you a little tingling sensation, kind of make your hair stand on end. It'll catch your attention, but it doesn't cause pain. So that's a very, very small current. Once you get into the 8 to 20 milliamp area, that's when it starts to hurt, and you'll feel it, and it'll jolt you a little bit. And really, I mean, 20 milliamps, it's not that much, but it will cause problems. Now, when you get into over 20 milliamps, what happens is involuntarily your muscles will clench, they'll flex. And this becomes a problem because if what you're holding in that hand is what's electrocuting you, you'll grip it and you'll hold on to it and you can't let go. No matter how hard you try, your brain signal is not going to be as strong as that electrical shock signal. That electrical shock is going to keep your hand holding on to that part, even though you're shocking yourself. So be very careful once you start getting up into the upper amperage ranges. This becomes a problem where you can't let go of what you're doing or you can't move to get away from whatever's shocking you. Over 100 milliamps, that's when you can cause cardiac arrest. That's when serious problems can occur, heavy burns at the minimum. So all current, just assume that all current is going to cause you trouble. If the circuit's live, treat it with respect because it can cause you trouble. Best practices, use good lighting. Now, this picture of a panel, that's not your typical one. That looks really well lit. It's got lighting inside of it. You go into most factories and they are not like that. The lighting on the floor is usually horrible. And then you're getting into a box that's shoved off in the corner somewhere, has even worse lighting. And you're trying to work in there. You're trying to fix something. You're trying to find and unhook things or insert things. What I would sometimes do is I'd use one of those LED headlamps that attaches to your head and that points right at whatever you're working on. Those work well. I have little light lamps that have a magnet on the bottom, clip inside of the panel. Gives you a lot better lighting. You'll save yourself a lot of frustration and the possibility of having a tool arc against something because you'll be able to see what you're doing. It's important. No loose clothing or jewelry. This is a big thing. If you're wearing a hoodie, has loose sleeves, baggy stuff, it's going to get caught on stuff. And that's what's going to pull your arm into a position you don't want it to be in. Jewelry, anything made of metal is going to conduct. So especially if like you're wearing a watch with a metal band, this is a short circuit maker. You get your hands into a panel and this clips onto something, hits two things, you're gonna You're going to cause problems. So it's best to just take off the watch, put it in your pocket, wear clothing that isn't loose. You're just you're taking on less risk that way. Um, have a plan. It's always a good plan. It's just like I told you with the tools, using the wrong tools. If you plan ahead, you're getting your tools ahead of time, setting them out where you can get access to them, having them set someplace where they're easily accessible, so you're not digging through stuff or putting your hands in places where you could end up getting shocked. So don't just set the tools inside the panel, or have a little rolling tray or something next to you that you can set things on. It just makes things a little bit more neat, a little bit less risky. Don't work alone. This is another important one. I've had plenty of times where I am working on something in a factory. There's a problem on one of the machines. I need to be able to see the problem, but the area where the problem's occurring isn't where the button is to activate it. So I'd walk over there, I'd activate the button to start the machine going, then I'd run over to the area where I need to see what's going on. And it's just a recipe for disaster. You could trip, fall into the machinery. You're trying to get there at the right time to see what's going on, or even to just fix it. Sometimes I need to activate a circuit to have something come down so that I can shut off the power at just the right time, so things are in the location I need to take them apart and do things with them. Just ask somebody around there. Most people they'd like to walk away from whatever they're doing and take a little break anyway. So it doesn't bother them much to just ask them, come on over and can you press this button when I tell you to? I just need to get these things done. Everything goes a lot more smoothly. You're not rushing. You're not taking risk. It's just easier all around. Assume all circuits are live. Just if you're working on something, it looks unassuming. I turned off the breaker. It must be fine. Don't assume. What you want to do is verify that and test. That's why you have your meter. You can test to make sure that there is no voltage on whatever it is that you're going to work on. And even though you have the power turned off on some things, you can see in this panel here, this guy's checking breakers and stuff. That breaker box is a lot like what you have in your house. And you can shut off breakers to circuits, but notice those 3 big wires going into the top. Even when you shut off the main breaker to that box, those 3 top wires are live all the time. So even though you think things are off, they may not be. So always test, use your meter, verify that things are off before you're working on something. Turning off the power isn't always enough. You think, well, power's off, I'm good to go. I'm going to dig into this panel and I'm going to start taking out some parts that are broke. Well, sometimes there is stored energy in things. Capacitors store electrical energy. There's springs that store mechanical energy. There's temperature. There's all sorts of things. So don't assume that just because power is off, everything's good to go. You want to check the system and make sure there's no capacitors within that system. And if there are, you want to discharge them safely so that you're able to work on that system without hurting yourself, because capacitors, they store energy, but it's not like a battery. It won't hold that charge forever. So if you really want to be safe, shut down the power to whatever it is you're working on and then go have lunch or something. Go 10 to 20 minutes at least with the power shut off. Those capacitors will naturally discharge. Or like I said, you can manually discharge them in a safe way to prevent arcs and prevent you from getting hurt with the system. Don't just reset a breaker. I see this all the time too. Power goes out in the system you're working on. You go over to check it out and the breaker's tripped. Don't just flip the switch back on. There's a reason why it happened. Try and figure out, why did it trip? Because if you turn the breaker back on, there's a good chance that you're just going to have it trip again, because whatever problem it is, if you haven't found out what the problem is, it's probably still occurring and it's going to trip it again. and could cause more damage to equipment that breaker is trying to protect. You could also electrocute someone who happens to be fiddling with the machine somewhere else, and you're over at the breaker box switching the breaker back on, and they get shocked. So try and figure out what is the problem to begin with. Why did the breaker trip before you just go and trip it back on? Now, when you figured out what the problem is, and you're going to go back to the breaker box and reapply energy to the circuit, make sure everybody who's around that equipment is aware that you're going to put power back onto it. Make sure they're clear of everything. You don't want somebody with their hand in the machine when the power goes back on. Everybody around that area needs to be made aware of what you're doing. It's one of the most overlooked things is just communicating with people, just telling them, I'm working on this. And we'll talk about lockout, tagout as an extra safety device as we go in future lectures. But communicating things is extremely important in safety. If everybody knows what you're doing, they're not likely to do something stupid during a moment in time when you're re-energizing the circuit or making things move again. Equipment often has two power circuits. Well, there's a power circuit, and that goes to controlling motors, other big equipment. That's where you get all your energy to really make things move. And there's usually a control circuit that's used to control, obviously, turn on and off the different components within the system. That usually runs at 24 volt DC or 120 volts AC, sometimes more. But they can be separate circuits. You shut off the power to one thing and you may have live wires going to other things. So just make sure that your controls and your power circuits are both turned off before you're working on something. In case of fire, this can happen when you're in this situation and things are getting out of hand. First thing you want to do is you want to find the disconnect switch. If the disconnect switch is too close to the fire, obviously you are more important than any piece of equipment. Don't risk yourself going for that disconnect switch. If it's away from the fire, obviously pull that switch, disconnect the electricity. It should stop the continuation of spreading the fire even worse. So, and if the disconnect switch is in a spot where the flames are and you don't want to risk, you might want to find the switch gear that feeds that box from another point upstream. If you can pull that breaker or pull that terminal switch, then you will disconnect the power to this box. So do whatever you can to try and shut the electricity off. Obviously, you want to report this to somebody. Make sure everyone's aware, especially the supervisor, so that any emergency action can be taken. Again, communication is super important. And then if there's a fire extinguisher nearby for electrical fires, grab that and try and put it out if it's safe to do so. If it's a dicey situation, you are more important than the equipment you're trying to protect. Run for the hills. If it's bad, don't stick around. But if you can, if there's an extinguisher nearby, use that and try and put the fire out. If somebody's being electrocuted, this happens. It can happen, and you can be around when it happens. It's a serious situation, and it's really hard to know what to do in the moment. Obviously, the easiest thing is to turn off the electricity to the circuit. That's if the disconnect is close to where you're at. Sometimes the disconnect might be a ways down the road. You gotta go down to the end of the machine to pull it, or you may not know where the disconnect is at. If it's nearby, obviously pull it. If it's a long way or you don't know where it is, you may have to take action other than that. Obviously, disconnecting the power is the best way to go. If someone's being electrocuted, oftentimes, like I said, they can be gripping onto whatever it is that's electrocuting them or leaning against whatever it is that's electrocuting them. And they need to be either knocked free or whatever they're holding on to pulled away from them. Don't use your hands. Don't come in contact with their body. Don't come in contact with the things that are electrocuting them. Don't use a metal object, something that doesn't conduct. If you can knock it away from them, knock them away from it or knock it away from them, one of the two, to prevent them from continuously being shocked. That's the best way to go. In a real extreme situation, obviously, again, you don't want to touch the person, but if they're wearing clothes that has slack to it, like a hoodie or a jacket or something that's loose that you can grab hold of with one hand, you can pull them away from it. So this, again, it's a split moment decision. You obviously don't want to come in contact with that person and get two people injured now. Protect yourself first. But if there's a way to drag them away from them because there's no other option of things to do, that's something that you can consider. Who's responsible for your safety? You. You're going to work on a system. Your buddy says, I'll go over there and I'll shut the breaker off. It'll be fine. I'll do that in the next 5 minutes and you're good to go. Don't trust it. You're going to have to go out over there and make sure things are shut down yourself. Make sure that things are locked out and tagged out, and we'll go over that in another lecture. And again, test the circuits before you work on them. You don't want to trust anybody, even though they're nice people and they have your interests in mind, but they can forget something or they can not do things correctly, and it's not their butt that's on the line, it's yours. So always verify things. Take your own safety into account and make sure that everything's covered to the extent that you want it to. All right, we're going to start in with basic electricity. So we'll learn how electricity functions within a circuit and how you can control that energy. We'll start out with a video here. This kind of really well illustrates how all this works, and then we'll start back with the lecture after this.
It's Paul here from the engineeringmindset.com. In this video, we are going to be looking at how electricity works. Now, this is pretty essential knowledge for any engineer, so we'll run through the basic parts of what you need to know. So let's start at the very basics, and for that, we need to take a look at the atom. Everything, including you, is made from atoms. All the materials we use are made from atoms. The materials are just different because the construction of their atoms are slightly different. The atoms are made from 3 particles, 2 of which are found inside the nucleus, and the third particle sits outside this. At the center of the atom, we have the nucleus. Inside the nucleus, we have the neutrons, which have no charge, and we also have the protons, which are positively charged. The neutrons and the protons are much heavier than the electrons, so these will stay within the nucleus. Surrounding the nucleus are different layers of orbital shells. These are like flight paths for the electrons. The electrons flow along these flight paths, much like a satellite orbits our planet, except that the electrons travel at almost the speed of light. The electrons are negatively charged, and they are attracted to the positive charge of the protons. The electrons orbit around the nucleus in these orbital shells, and there are a set number of how many electrons can be in any one orbital shell. The number of protons, neutrons, and electrons an atom has tells us which material it is. Atoms hold on to their electrons very tightly, but some materials will hold on to them more tightly than others. The outermost shell is known as the valence shell, and in this shell, some materials have loosely bound electrons which can flow to other atoms. Atoms which can pass electrons are called conductors, and most metals are conductors. On the other hand, atoms which do not have free electrons, and so they can't pass electrons between other atoms, are known as insulators, and these are things like glass and rubber. Now, we can combine these materials to safely use electricity by having the conductor in the center, which allows electrons to move, but surround this with an insulator to restrict where they can flow to, i.e. not into us, which keeps us safe. If we look inside a slice of copper cable at the free electrons surrounding the nucleus of the copper atom, you'll see that the free electrons are able to move to other atoms, but this happens randomly in any direction. If we then connect the slice of copper cable to a closed circuit with a power source, such as a battery, then the voltage will force the electrons to move, and these will then all flow in the same direction to try and get back to the other terminal of the battery. When I say circuit, this just means the route which electrons can flow along between the 2 terminals, the positive and the negative, of a power source. So we can add things into their path like light bulbs, And this means that the electrons will have to pass through this in order to get to the other terminal. And so we can use this to create things such as light. The circuit can even be open or closed. In a closed circuit, that means the electrons can flow around, and in an open circuit, this means that the electrons are not able to flow. Voltage is a pushing force of electrons within a circuit. It's like pressure in a water pipe. The more pressure you have, the more water can flow. The more voltage you have, the more electrons can flow. But what does a volt mean? Well, a volt is a joule per coulomb, and a joule is a measurement of energy or work, and a coulomb is a group of flowing electrons. We'll have a look at what a coulomb is in just a second though. So a 9-volt battery can provide 9 joules of energy in the form of work or heat per group of electrons that flow from one side of the battery to the other. In this case, the current of electrons flow from one side of the battery through the LED light bulb, which produces light, and then the electrons flow to the other side of the battery. Therefore, 9 joules of light and heat is produced by the light bulb. Current is the flow of electrons. When a circuit is closed, it means electrons can flow, and when the circuit is open, no electrons will flow. We can measure the flow of electrons just like you can measure the flow of water through a pipe. To measure the flow of electrons, we use the unit of amp. 1 amp means 1 coulomb per second, and 1 coulomb is a group of electrons. The group is incredibly large and is approximately 6,242,000,000,000,000,000 electrons, and that has to pass in 1 second for it to equal 1 amp. That's why electrons are grouped together and just called amps to make it easier for engineers. Resistance is a restriction to the flow of electrons in a circuit. The wire which carries the electrons will naturally have some resistance. The longer the wire, the greater the resistance. The thicker the wire, the lower the resistance. Resistance to the flow of electrons is different for each material, and the temperature of the material can also change the resistance to the flow of electrons. Electrical circuits use specially designed components known as resistors to purposely restrict the flow of electrons. This is either to protect other components from too many electrons flowing through it, or it can also be used to create light and heat, such as in an incandescent light bulb. Resistance occurs when electrons collide with atoms. The amount of collisions is different from one material to another. Copper has a very low collision rate, but other materials such as iron will have much more collisions. When collisions occur, the atoms generate heat, and at a certain temperature, the material will then start to produce light as well as heat, which is how the incandescent lamps work. When a wire is wrapped.
Okay, so that was kind of an overview of probably what you've learned in your physics class, basic things about what electricity is, how it moves. So we're going to kind of review some of that. Volts is also known as electromotive force. This tends to be what electricians refer to it as, electromotive force. It can be thought of as a pressure, kind of like with water. The higher the pressure, the more forceful it can move the current through a hose or whatever it is that you're doing. So current is like kind of the equivalent of pressure for water. It has a polarity. That polarity is what determines which way the current flows from one end of the potential difference to the other. So it will follow that. Now, the symbol for voltage is either V or E. That depends on whether you're an engineer or an electrician. Electricians tend to use E for electromotive force. Engineers use V for voltage. So yeah, the direction of which way it goes is dependent on the polarity, and that can change in alternating currents. So we'll get into that later. Amperage. It's measured in amperes or amps. It's the rate of flow of electrons. It's similar to the rate of water flow, and that's why it's often referred to as current. So the flow of electrons is referred to as current as a standard. Current flows from positive to negative for engineers. Electricians, again, have to be different. They go from negative to positive. And the electricians actually have it correct because electrons do flow from the negative potential to the positive, but when they first were starting to experiment with electricity, they decided to call the flow of current from positive to negative, and that's what engineers still use, which is okay as long as you're consistent. As long as you always do all your calculations with the same reference of positive to negative, it will work out. And if you're an electrician and you go from negative to positive, that's fine as long as you always consider it to be that way and do all your calculations with it in that way. So just keep that in mind that electricians will think of things slightly different than engineers will. I is the symbol for current, which has a unit of amps. Why I? It's actually an odd thing. Back in the day they considered current to be the intensity of current flow. So they used I in their equations for measuring the rate of current flow. Ohms of resistance. It's a restriction to the flow of current, kind of like a kink in a hose. The resistance, it forms a drop in voltage across it. And this is a little difficult concept to kind of get across, but if you think of a hose with a kink in it, if you apply a certain amount of water pressure to that hose at the beginning of the kink, it's going to build up pressure, and there'll be more pressure there at the beginning of the kink. But as the water flows through that restriction and comes out the other end, there'll be a little bit less pressure. And so that difference of pressure on one end of the kink to the other is the pressure drop. And with electricity, it's considered the voltage drop. So as current flows through a resistor, it will create a drop in voltage on the other end of it once it gets through it. R represents resistance in equations, and that makes sense. It's R for resistance. The symbol is the omega sign, which stands for ohms, which is named after the guy that invented it. Now, one thing with all these different units, all these different concepts, when you are using the measurements you take in equations, you always want to use base units. Now, by that, I mean, you can measure ohms, you can measure milliohms, you could measure microohms, you can measure kiloohms or mega ohms. If you measure it and write it down that way, that's fine. But if you're going to use it in an equation, you have to convert it to its base unit of ohms. And that's the same for volts or amps. If you're going to have an equation that uses volts, it's going to have to be in volts, not millivolts or kilovolts. So keep that in mind, because otherwise your answers will be off by a factor of 1,000 every time you're doing calculations or more. Watts. This is electrical power. This is how much work is done and consumed by the loads in the circuit. So it is a measure of work done by the electrical current that's flowing through it. Each load in the circuit will consume a certain amount of power, and the total power consumed by the entire circuit will be the sum of all those different loads on the circuit and how much they consume. P is a representative for power, and its units is watts. So now we'll be mostly dealing with DC circuits to start out with. That is when the current flows in only one direction, from positive to negative. But there also, we will deal with later, the concept of AC, or alternating current. That's when the polarity, the voltage polarity of the circuit flips back and forth. It switches places, which causes the current to flow in different directions back and forth. It follows the polarity of the voltage. When the voltage alternates, the current will alternate. So even though it's AC for alternating current, it's also alternating voltage. Electrical symbols. So in order for everybody to be on the same page, we all use a universal set of symbols to represent things, because it's too much of a pain in the butt to try and draw a resistor or draw a transformer or whatever electrical component you're using. It's easier to use symbols. They become more standardized and universal. They make it easier to read also. So now these symbols tend to be the same, but there's some variations you get, especially in different countries. They tend to have different conventions, but You can see for resistors, there's a sawtooth line there. That's the usual representation for a resistor, but you can also have just a rectangular box there. If it's a box, oftentimes they usually have the resistance value either printed in the box or beside the box. Switches, there's all sorts of symbols for switches. They tend to show graphically what points will get connected when the switch is thrown from one position to another. It'll show how many different positions you could throw the switch into, and then how many different poles will connect different terminals when you throw the switch. Push buttons. They can be sometimes a little bit different. We'll go into several of those eventually. You can see in the one to the left, when you push the button, those two terminals are normally not connected together, but when you push the button, it will touch both of those contacts and allow current to flow between them. The one to its right, if you notice, the button, when unpressed, is actually connecting those top two terminals. Those would be considered your normally closed contacts. Then when you push the button, it's going to disconnect those top two terminals and connect the lower two terminals together. Those are considered your normally open contacts. And a lot of switches on the factory floor are going to have both normally open and normally closed contacts in them. It's a way for you to control things in different ways. Sometimes you want something to activate when you push the button. Sometimes you want things to deactivate when you push the button. So that would depend on which one you're using, normally closed or normally open contacts. Your power supplies could be a battery. It could be DC, which would show polarity, which end of it is positive, which end is negative, or it can be AC, which obviously the polarity changes from moment to moment. So it just shows that it's an alternating current with a little sine wave symbol there. Battery is just a series of long and short lines. Those are used to represent, I think what they were going for is like a coin battery. One of those coin-shaped little batteries has like a big base and then a little bit of a protrusion on the top part of it. And you can take several of those coin batteries and put them together to sum up the voltage to get a larger voltage. So it's usually drawn in that manner. Grounds can be drawn in a couple different ways, but they all mean zero potential, where everything is common to one another. Capacitors and inductors, we'll get into those in future lectures. They can have slightly differing symbols. They're pretty similar, though. It's not too hard to figure them out. Fuses, they show it with the rectangular box, a little line going through it, just like the little filament that will burn out when the fuse is overloaded. Or it has a symbol that looks kind of like the glass tube with the little metal caps on the end. So that's why they draw it in two different ways. Lamps can take on several different symbols for it. The least obvious is the one in the center with the X in the middle. But the other two kind of look like either a light bulb or something that's shining. Diodes we'll also go over later, but they can have slightly different symbols that would be put in there. Transformer shows two inductors kind of side by side with a couple lines in between, which are meant to indicate that there's a ferrous core in between them to help improve the induction process between the two coils. Terminology, just so we all use the same words. A load is the element that's consuming the energy within the circuit. And I've mentioned that several times. There's anything you hook to it that is going to use the power that you're putting through the circuit is going to be considered a load. But also, you can consider a load to be the amount of current that's flowing through that circuit. So sometimes someone will ask you, what kind of a load is that pulling? And what they mean when they're asking that is how many amps are you pulling to that circuit so that you can size things correctly. The amount of load on a circuit really depends on, it gives you the criteria that you're going to need to determine what size parts to get, like wire size, relay sizes. All of the components have to be rated to handle that kind of a load or amperage. A source is just a source of energy, whether it's a battery or a power supply or the outlet in your house. So your source is just where the energy comes from. A short is just wherever two wires connect together to create a connection there. A short circuit is when it's this more specific instance of when you are connecting two parts of a circuit together with no resistance that has a potential across a voltage there. So you are shorting that part of it out and causing what it tries to do is create infinite current going through it because there is no resistance. So obviously that's something you want to avoid. It's going to cause you some trouble, cause a lot of heat, cause a lot of sparks. So a short circuit, though, is specifically an instance where you are taking two potentials, connecting them together, and causing there to be no resistance and huge amounts of currents caused. An open circuit is when the circuit conduction path breaks, when it's separate apart. Now, a good example of that would be a fuse. When a fuse blows, the little filament in it burns out, goes away, and then there's no longer the ability to conduct electricity through there. So that would end up creating an open circuit. And just as a side note, most of the time when components fail, they tend to fail in an open configuration. Doesn't mean that they won't start a fire in order to get to that point, but things tend to fail in open. There's rare instances where it can create a short circuit when it fails, but luckily things tend to fail in an open circuit, which tends to shut things down anyways. Hot wire is a wire that has electrical potential on it, just for note. Wire gauge, we'll get into this more in a lecture about conductors because there's a lot to do with conductors. Actually, you wouldn't think that there would be so much about wires to learn, but there's a lot there. But in general, the wire gauge is the measurement of its size and capacity. And we tend to use AWG as American wire gauge to denote that. It's usually a number that represents how big the wire is and what its current carrying capabilities are. This little chart shows a good example of it. In the lower right corner, you can see that 14 gauge wire is a smaller wire that can handle 15 amps. This is what's run through most of your house. Most of your outlets, most of your switches, your lighting and all that are run off of 15 amps. And in your breaker panel, you'll see a lot of 15 amp breakers in there. Those are for general lighting and general power throughout your house. Notice if we go to a smaller gauge of 10, that is a bigger wire slightly and can handle 20 amps. These would be routed in your house for your kitchen and bathroom and maybe your garage for higher load devices like hair dryers and blenders and other things. So it's able to handle 20 amps. You'll see those 20 amp breakers in your panel box, and that's what those are for. You'll see a few 30 amp breakers in your panel box that they'll have 10 gauge wire going to it. It can handle 30 amps. That would be for stoves and ranges and air conditioners, things like that. But you notice the wire gauge keeps getting to be a smaller number for bigger and bigger wires. Eventually you get to 0. So what if you want a wire bigger than 0? Well, they come up with a convention to go even bigger than that by using multiple zeros. So you can see there's one called, it's a 1/0. That means 1/0. That means single zero. Aught means 0. So that's a single 0 sized conductor, and it can handle 150 amps. Something bigger would be 3/0. With the 3/0, that represents 3 zeros, which means it's even a bigger gauge, and that can handle 200 amps. So you could have 5/0, you could have even bigger and bigger and bigger wires. So that's just the convention there, but we'll get into that more in another lecture. DC circuits, that's what we're going to start out with. A circuit is a power supply and conductors and a load. It's that simple. You need the supply of power, you need a way to get it to the load, and you need the load itself. Here we have all three plus a switch to control it. Current flows, like I said, from positive to negative. So in this instance, this is the way the current's going to flow through the system. Ohm's law. So this is our first equation that we're going to work with. Voltage equals current times resistance. Again, like I said, you're going to want current to be in amps, not milliamps. You want resistance to be in ohms, not kilo ohms. When you do those calculations, and you can find voltage based on those two other values. This equation obviously can be rewritten to solve for other things. You could have current and resistance are things that you could find by just manipulating the equation. So usually if you know two of the different components, you can find the third through these equations. Power is current times volts. Simple equation. Again, they have to be in their base units. So here we can use Ohm's law to figure out how much current is going to flow through this particular circuit. Let's say you have an incandescent light bulb. You can use your meter to measure the resistance of that light bulb. And let's say it's 6 ohms. You hook it up to a car battery. It's got 12 volts. You can calculate to predict how much current is going to flow through that circuit when you close the switch. As it shows there, current equals voltage divided by resistance. You got your 12 volts divided by 6 ohms will give you 2 amps. So if everything's exact in the circuit, you can expect 2 amps to flow. So that's how Ohm's law can be used to solve for one thing if you know two others. Here, let's say you're hooking up a piece of equipment. You don't know how much resistance it has. All you know is that you're hooking up to a 12-volt battery, and you hook up a meter to it, and you notice it's pulling a half an amp. You can calculate how many ohms of resistance that particular piece of equipment has by just taking the voltage, 12 volts, divided by the current, which is a half an amp, divide it out, and you've got 24 ohms. So that's a way to find out the resistance of an object that you don't know what the resistance is. Now we got another quick video to illustrate series circuits. So we're going to get into that. Then we'll come back to the lecture when that's done.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at DC series circuits. We'll cover voltage, current, resistance, and power consumption, as well as using a multimeter and a chance for you to test your knowledge at the end. When we connect components in an electrical circuit, we can connect them either in series or parallel, or we can combine these to make a series parallel circuit. We're going to start with the series type, which is the most basic, but we'll cover the other types in other tutorials. Do check those out, links down below. So if we place two components in a line end to end, or with some wires in between, then these are connected in series. The electrons only have one path they can take, so they will all flow through each of the components. By the way, in these animations, I use electron flow, which is from negative to positive. You might be used to seeing conventional current, which is from positive to negative. Electron flow is what's actually occurring. Conventional was the original theory, but it's still taught because it's easy to understand. Just be aware of the two and which one we're using. Resistance in series circuits. Each component will have a certain resistance. The resistance opposes the voltage being applied. We measure resistance in a unit of ohms. In series circuits, we find the total resistance for the circuit by simply adding together all the resistances. We label each resistor with a capital R and number them R1, R2, R3, etc. The total resistance is shown with a capital letter R and a subscript T, which represents the resistance total or the total resistance. To calculate the total resistance of a series circuit is super easy. We simply add together the resistance value of each resistor. Let's say we have a circuit with a single resistor. That's our R1, and this has a value of 10 ohms. So what is our total resistance? Well, that's easy. The total resistance is just 10 ohms. If we then added a second resistor, R2, with 5 ohms of resistance into the circuit, the total resistance is now 15 ohms. That's because 10 ohms plus 5 ohms. If we added another 5 ohm resistor, then the total resistance is now 20 ohms. In reality, the wires too will add some resistance, but this is very small. You might need to account for this depending on how accurate your design needs to be. Current in series. Current is the flow of electrons. It's like water which flows through a pipe. The higher the current, the more electrons are flowing. We measure current in the unit of amperes, but engineers tend to shorten this to just amps. Now we have covered current in detail in our previous video. Do check that out, links down below.
We measure current by placing an ammeter into the circuit for the electrons to flow through. This is like a water meter in the sense that water must pass through it for us to measure it. We can connect a multimeter into the circuit to also read the current. The multimeter must be placed into the circuit for us to take a reading, because the current will flow through this. The meter will add some resistance to the circuit, but it's such a small amount that we can usually just ignore this. If you don't have a multimeter yet, then I highly recommend you get one. They are essential for troubleshooting and also building your understanding. I'll leave some links down below for which one to get and from where. We can calculate the total current of the circuit by dividing the voltage by the resistance. So if we connect a 10 ohm resistor to a 9 volt battery, 9 volts divided by 10 ohms gives us 0.9 amps. If we added another 5 ohm resistor to the circuit, that gives us 15 ohms of resistance. So 9 volts divided by 15 ohms equals 0.6 amps. And if we added another 5 ohm resistor, that gives us 20 ohms of resistance. So 9 volts divided by 20 ohms equals 0.45 amps. So we can see that as we add more resistance to the circuit, the current reduces, so less electrons are flowing, and that means we can do less work. We can visualize that by connecting an LED with a resistor into a circuit. The higher the resistance, the dimmer the LED will be. We can also use resistors to protect components in the circuit. If I use a 100 ohm resistor with a 9 volt battery, the current will be around 0.09 amps or 90 milliamps, and that will be too much and it will blow the LED. If I use a 450 ohm resistor, the current will be around 0.02 amps or 20 milliamps. So the LED should be okay. If I use a 900 ohm resistor, the current will be 0.01 amp or 10 milliamp, and the LED will be very dim then. In a series circuit, the current is the same throughout the entire circuit. That's very important, so do remember that. If we place the meter here or here, we will get the same reading. That's because there is only one path for the electrons to flow and they will all move together in the same direction, so the current must be the same. It doesn't matter where we measure or where we place the resistor, even if we swap the order of the resistors. The current will be the same anywhere in a series circuit. Voltage in series. Remember, voltage is the pushing force of electrons. It's like pressure in a pipe. The higher the pressure, the more water can flow. The higher the voltage, the more electrons can flow. We can see that by varying the voltage to a lamp as illustrated here. The lamp increases in brightness as the voltage increases. When we measure voltage, we're measuring the difference or potential difference between 2 points. If we read across a 1.5 volt battery, we get a reading of 1.5 volts. But if we try to measure the same side, we wouldn't read any voltage. We can only measure the difference between 2 points. If we place a 9 volt battery into the circuit, we apply 9 volts to the circuit. We can increase this by wiring the batteries in series. So if we place two 9 volt batteries in a circuit in series, then we get 18 volts. 3 9 volt batteries will give us 27 volts. Let's take a 9 volt battery and add an R1 resistor of 10 ohms to the circuit. If we use a multimeter to measure across the resistor, we get a voltage reading of 9 volts. If we add another 10 ohm resistor, we get a reading of 9 volts across the two resistors, but we get a reading of 4.5 volts if we measure across either of the resistors individually. So the resistors are dividing the voltage. If we replace the R2 resistor with a 5 ohm resistor, the total voltage would again be 9 volts, and that's what we see if we measure across the two resistors. But if we measure across the 10 ohm resistor, we see a voltage of 6 volts, and if we measure across the 5 ohm resistor, we see 3 volts. We'll look at why that is just shortly. If we added another resistor, R3, with 5 ohms into the circuit, we again get a total voltage drop of 9 volts across the three resistors. Across the R1 10 ohm resistor, we read 4.5 volts. Across the R2 5 ohm resistor, we read 2.25 volts. And across the last R3 5 ohm resistor, we again see 2.25 volts. We can combine these readings to find the voltage at different parts of the circuit. For example, if we measure from the battery across R1, we see 4.5 volts. If we measure from the battery across R1 and R2, we get 6.75 volts, because 4.5 plus 2.25 volts. So unlike current, where it's the same throughout the circuit, the voltage will be different throughout a series circuit. This shows us that the voltage is reduced by each resistor, so the resistor creates a voltage drop. That's the purpose of the resistor, to reduce the voltage or the pressure. What's happening is the resistor creates a more difficult path for electrons to flow through, and as they flow through, they will collide with other electrons. This collision will convert the energy into heat. the same amount of electrons will enter and exit the resistor. They will just have less energy or pressure as there's been a voltage drop. We can calculate the voltage drop across each resistor individually by multiplying the total current in the circuit by the resistance of each component. Remember, in a series circuit, the current is the same anywhere in the circuit. The total voltage drop will be the total of all the individual voltage drops combined. The first circuit, there was a 10 ohm resistor by itself. The circuit had a current of 0.9 amps, so 0.9 amps multiplied by 10 ohms equals 9 volts. The voltage drop across the resistor is therefore 9 volts, and that's the same as the voltage source. The second circuit had a 10 ohm and a 5 ohm resistor together. So the first resistor voltage drop is 0.6 amps multiplied by 10 ohms, which gives us 6 volts. The second resistor was 5 ohms and the current was the same, so 0.6 amps multiplied by 5 ohms equals 3 volts. The total voltage drop is therefore 6 volts plus 3 volts, which gives us our 9 volts. The third circuit has a 10 ohm and two 5 ohm resistors. The circuit had a current of 0.45 amps. So R1 is 0.45 amps multiplied by 10 ohms, which gives us 4.5 volts. R2 and R3 will be 0.45 amps multiplied by 5 ohms, which gives us 2.25 volts on each. The total voltage drop is therefore 9 volts, which is 4.5 plus 2.25 plus 2.25. Power consumption.
Okay, that was a lot in a very short amount of time. They really condensed that down. So we're going to go through it in a little more detail, just to slow it down a bit and go through it. So in a series circuit, there's only one path, and that's one of the main things you're going to have to remember is that once the electricity comes out of the power supply, there's only one place for it to go. It has to go through that one path, which means it has to go through each one of those 3 resistors. Now we're going to solve for current, voltage, and power for each one of these resistors. We have 3 of them here. We assign values of resistance to each one of the resistors, and we'll just work through a problem so that we can find all the information we need to know about this circuit and all the different values for each one of these resistors. So the total equivalent resistance for the circuit is just adding them all up. Your R equivalent or your R total is R1 plus R2 plus R3. So you add the 10 ohm, the 20 ohm, and the 30 ohm resistors together, and you end up with 60 ohms. So these 2 circuits, as shown, are really equivalent as far as the power supply is concerned. It doesn't know that you have 10 resistors hooked to it or 2 or 1. So if you have 3 resistors with those values hooked up to the power supply, it's going to react the same as if you had 1 resistor with 60 ohms hooked up to it. So being able to simplify it down to a single total resistance allows us to use Ohm's law to then calculate current through that equivalent circuit. So if we have 12 volts and we know that the equivalent total resistance of the circuit is 60 ohms, then we can find out how much current total is going to come out of that power supply. So it's just the total voltage, which is 12 volts, divided by the 60 ohms gives us 0.2 amps. So the power supply is set at 12 volts, and it will give off 0.2 amps to the circuit. So now we know what the total current coming out of the power supply is. It's 0.2 amps. We can go back to our original circuit with the 3 resistors and now calculate what the voltage is going to be across each one of those resistors, because we have current and we know that the current is going to be the same throughout the entire circuit, and we can calculate the voltages across each one of those resistors. So you can kind of think of this circuit almost like a hose with 3 kinks in it. And if I pour a gallon of water into one end of the hose, how much water is going to go through the first kink? Well, a gallon's going to go through that first kink. How much will go through the second one? A gallon. Third one, a gallon. And what's going to come out the other end? A gallon. So the current is the same throughout. So this 0.2 amps that's coming out of the power supply will be what goes through each one of those resistors. So now, knowing the current that's going to go through resistor 1 here, that's a 10 ohm resistor, we can find the voltage that will be across just that one single resistor. It'll be the, well, here we have this one shows that all the currents are the same. But for resistor 1, if we take the current times the resistance, which we know the current to be 0.2 amps going through resistor 1, we know the resistor 1 value is 10 ohms, we get the 2 volts will be what results across that particular resistor. And if you think of it again as an equivalent of a water hose with a kink in it, you're going to have a certain amount of pressure on one side of that kink, and on the other side, there'll be a different amount of pressure. And for this instance, with the current flowing through it, you're going to have a difference in pressure of 2 volts through that first resistor. Resistor 2, same thing. You have the same current going through it of 0.2 volt or 0.2 amps, but now you have 20 ohm resistors, so that gives you 4 volts when you multiply those together. Third one, same thing, same current, 0.2 amps times 30 ohm resistor gives us 6 volts. So now notice each one has a different voltage across it, but all 3 of them added together ends up equaling the applied voltage of 12 volts. So we can say that the circuit of these resistors is dividing up that applied voltage of 12 volts into separate amounts across each one of those resistors. They should all add together and equal the applied voltage. Notice which resistor has the biggest voltage drop across it. That's the biggest resistance or ohm value of 30 ohms. It's because it's like a bigger kink in the wire. So it's going to end up having a bigger pressure difference on either side of that kink. So the one with the higher resistance in series ends up getting the most voltage dropped across it. Now we'll do a power. Power is pretty simple. Once you know the current going through them all and you know the voltage across each one of those resistors, now we can calculate the amount of power that each one of those resistors is going to consume in watts. The first resistor we know has 0.2 amps flowing through it. We calculated it to have 2 volts across it. So we multiply those two together and we get 0.4 watts. Same with resistor 2, with the same current, 0.2 amps times 4 volts across that one gives us 0.8 watts that resistor is going to consume. Same for the third one, got the same current times its voltage of 6 volts will give you 1.2 watts across it. Now the total amount of current or total amount of power that circuit is going to consume is going to be the sum of all those individual power wattage from each one of those resistors added together. Notice that the one with the highest resistance also ends up consuming the highest amount of power. Now, another thing to notice is that the total power consumed could have also been calculated by the fact that you know that the power supply is 12 volts and it's putting out 0.2 amps. You take that voltage times that current and you get the total consumed power in watts. So if you take 12 times 0.2, you'll end up with the same number as if you added up all those individual powers for each one of those resistors. So now we know pretty much everything we need to know about this circuit. We were able to find that we knew the resistances of each one of the resistors individually. It was given to us, but we are able to find the total resistance by adding them together. The amperage we calculated after reducing that circuit down to a single resistor, so we could calculate the total current coming out of the power supply, and we know that that's equal throughout, so all of them have 0.2 amps going through them. The voltages across it were just calculated using that current and the resistor value of it, so we got separate voltages for each one of those resistors, which all added up to be the applied voltage of the power supply. Power was just current times voltage. Again, those just calculated out. Now, one thing you can notice is that with resistors, when you're buying them, you buy them for a particular ohm rating, right? You also need to buy things based on a rating of what it can handle, how many watts it's able to consume. Because some resistors can be very, very small, and they will get overloaded if you try and put too much current through them. You can get resistors that are the size of my thumb that will handle a large amount of current. So you do want to buy your resistors based on not just the ohm amount. You don't just buy a 10 ohm resistor. You got to buy a 10 ohm resistor at a certain wattage. Now those tend to be sold in eighth watt, quarter watt, half watt, 1 watt, 3 watt, 5 watt, whatever. And if you notice from the measurements that we calculated for resistor 1, I could get away with a half watt resistor. It's only consuming 0.4 watts, so I could buy a half watt 10 ohm resistor. R2, if I bought a half watt resistor, it's likely going to melt or catch fire. So the rating for power consumption is important when you're buying certain components. Notice R3 also, again, you would need over more than 1 watt rating. You probably need to buy a 2-3 watt. It's fine if you put a 10 watt resistor in there. Anything, as long as you're not overloading the power rating of it. Voltage drop, we kind of went over that. Each one of those resistors creates a drop in voltage, but we can go through and look at different points within the circuit to determine what would be the voltage at those particular points. The voltage at point 1, it's right at the power supply, so we know it's 12 volts because that's what's coming out of the power supply. That point is actually touching the positive terminal of the battery. So we put in 12 volts there under point 1. What's point 2? We know that resistor 1 had a 2 volt drop across it. So we know that at point 2, you're going to drop 2 volts off of that 12 volt rating on the other side of the resistor. So we should end up with 10 volts at point 2. Put that in the diagram as 10 volts. So now what do we have at point 3? Well, there's going to be another 4 volts across that resistor 2 that it's going to drop down. So we're going to go from 10 volts minus the 4 volts. It should be 6 volts at point 3. Now, we know that the last resistor has 6 volts that we calculated across it. So by the time it goes from point 3 to point 4, it should have 0 volts, which makes sense because the negative terminal is always considered a 0 volt terminal. It's the common. So that's how voltage drop works. At any different point in that circuit, you can observe and read a different voltage reading than what the power supply is providing. And oftentimes you will use resistors in this way to create a smaller voltage from the original power supply. Let's say you're hooking up to a 12 volt battery, but you need to power a circuit that only runs off of 5 volts. Well, you can divide up that voltage to get the voltage you need, picking the right resistors for the job. All right, we're back. Now we're going to deal with resistor color codes. This is a convention that they use for marking resistors. Rather than writing digits on it, they just put color bands on it. It's slightly helpful when the resistor gets really small. It's too hard to print a number on it, or it'd be hard to read. So the color bands tend to be what they use for them. There's an example of 2 different resistors. Now, with the color code bands, you've got 4. Sometimes you'll have 5. But with this one, we'll just stick with 4 for this example. But one of them will end up being either a gold or a silver band. Those represent tolerance. Tolerance is how much play in the value that you can get. Let's say that a resistor is marked to be 100 ohms. Well, they can't manufacture them perfectly. So there's going to be a little bit of variation. It'll rarely be exactly 100 ohms. So the gold or silver band is going to tell you, well, how close are we going to get to that 100 ohms that's marked on it. So a gold band means it's closer. It'll be 5%, plus or minus 5% is what you should find in any resistor you pull out of the bag for those. Or a silver stands for 10% variation. Plus or minus 10%. Resistors, you can get ones that are really, really accurate. You can get them 1%. You can get them less than that if you want. You just end up paying for that. The more tight the tolerance, the higher the cost ends up going up. And just as a side note, capacitors and inductors, they're even more difficult to manufacture perfectly. So those can easily have 20% tolerance on those. The value that they end up being versus what they're marked can vary quite a bit. So just be aware of that. But with the resistors, it uses these color bands to express that. And gold is obviously better than silver. It's just a little bit tighter tolerance. You're going to get a more accurate resistor based on what it's marked. Now, each one of those color bands, other than the gold, they're going to represent numbers. So we got a little chart here that shows the value, the number value associated with each color band. This one happens to have green, blue, and orange. Those three are represented by the numbers 5, 6, and 3. So now what do we do with those three numbers? Well, the first two color bands, the green and the blue there, those are going to be just straight up digits. You write those two down. So you have 5 and 6. So you just write down 5 and 6. And then the third color band is going to be how many zeros you add to the end of that. So the orange band stands for 3. So we're going to add 3 zeros to it. So that 56 is going to turn into 56,000. So this resistor is marked to be a 56,000 ohm resistor with a 5% tolerance. So that's how you read the color codes on a resistor. We can go through another example here. We have brown, black, brown with a gold stripe on it. So the first two digits are going to be brown and black, which are 1 and 0. And the third color band is brown for 1. So that means we're going to add 1 0 to the end of that, which means this is a 100 ohm resistor with 5% tolerance. So it's pretty straightforward. We'll go through another example here. The first two digits are 4 and 7 for yellow and violet. Violet means purple. So you got 4 and 7, and then the third color band is black, which means 0, which means we'll have 0 zeros added onto it. So this one is rated for 47 ohms, and it's at 5% tolerance for the gold band. So that's what happens when you run into a black band on the third value. You're just not going to add any zeros to it. So the tolerance, so we can actually calculate that if you want. This example shows that 100 ohm resistor, and if it has a gold band, it means that it's plus or minus 5%. Well, 5% of 100 ohms is 5 ohms. So that means that if you have a bag of 100 ohm resistors with those stripes on it, you pull any one out of it, it's going to be somewhere between 95 and 105 ohms. So that's specifically what the tolerance band means, is that there will be some variation. Most of them will be pretty close to 100, but they can vary a little bit, but they shouldn't be outside the range of 95 to 105 ohms. Okay, now notes on this lecture are going to be available on the e-learning website. It's going to cover this material that we've gone over. It should have some more example problems to solve through. This PowerPoint I'll also put on also as a file, a PDF file that you can download if you wanted to look at that. Obviously, the video you can watch more than once if you need to. So there's going to be a quiz on the e-learning site that you'll want to take. I've given a long leeway of time for when it needs to get done, but it's kind of in place of the lab. You go on there, pop into the quiz, it will grade itself. It's all multiple choice. There's a couple fill in the blanks, but they aren't too bad. Fill that out. It won't be graded immediately. It automatically grades the multiple choice part, but I'll have to grade the short answer by hand. There's also homework assignment that's going to be in the e-learning site. That what you can do is download that, print it out, fill out, answer all the questions, and you can hand that in when you come in to the in-person lecture next week. If you have any questions, my email address is there. My other information, it's all on the syllabus as well, which is also available. I'll put that in there in the e-learning site as well. So that's our first lecture. Next week, it's going to be, there's no lab this week. It'll be the homework assignment and the quiz in its place. But next week we will be in person, and there will be a lab after that. So get ready for that. And I look forward to seeing you next week.